Assalamualaikum. My name is Nur Sujana binti Bubakar. Today we are going to present about our experiment 6, High Performance Liquid Chromatography, which is HPLC. So this is our introduction. HPLC utilizes a liquid mobile phase to separate the components of mixture, which is incredibly versatile because of its ability to easily separate a wide variety of chemical combinations, including non-volatile and thermally unstable chemical. For example, organic, inorganic, biological samples, manufactured or natural polymers, and thermal molecules. And what they use HPLC is like pharmaceutical, food analysis, environmental testing, and research. Okay, next, for HPLC application, like any compound with solubility in a liquid that can be used as a mobile phase. And then about analytical or preparative, like highly purified compound in small or large quantity. Then application like include analysis of sugar, pesticide residue, organic acids, lipids, amino acids, toxins, and vitamins. Okay, then this is our objective for our experiment to determine the retention of a standard solution, and then to identify caffeine in the soft drink sample, and last is to determine the amount of caffeine in soft drink sample using the response factor method.
Hello guys, hi, my name is Farhan and now I will explain to you guys about the method in HPLC. First, in chromatography, the separation of a different component from a mixture occur through a process of partitioning between two phases. First, the mobile phase, and the second one, the stationary phase. Okay, and alright, we go with the first process, which mean injection process. Okay, we begin by injecting the sample or analyte onto the top of the chromatographic column, and the sample contain a mixture of a different component which we aim to separate. Alright, and the second step is a column setup. The column itself is packed with a stationary phase, which could be a solid or a liquid phase, depending on the type of chromatography being performed. Alright, the column is usually long and narrow to allow for the separation of the component over time. Alright, and then we go with a mobile phase flow. Once the analyte is injected into the column, the mobile phase, which a liquid or gas, is continuously pumped through the column. The mobile phase acts as a carrier, transporting the analyte through the column. As the sample through the column, the individual component interact differently with stationary phase. Some component are more attracted to the stationary phase. Alright, and we go to the next process, which means separation of component. The result of this difference in movement is separation. Each component in the sample will travel through the column at a unique speed. Alright, actually is the unique speed is depending on its affinity for the mobile and stationary phase. Okay, and then we go with elution process. Eventually, each component elute from the column, meaning it exits the column at a specific time. As the analyte elute, they reach the detector. Now we almost at the ending of this method. Okay, I go with a chromatogram. The chromatogram display a peak corresponding to each elute component. The position of the peak along the x-axis represent the time it took for the component to elute from the column, known as RT, which mean the retention time. Alright, the height or area of the peak is proportional to the amount of the analyte present in the sample. Alright, this chromatographic data allows Actually, this chromatographic data allows we or us to identify and quantify the component of the mixture by providing valuable information about its composition. Actually, every piece in the display will represent something. Lastly, what I want to conclude from this experiment is chromatography is a essential technique in a many scientific field. By enabling the analysis of a complex mixture, the process involves injecting a sample, separating its component as they pass through the column, and using a detector to record and visualize the result in the form of chromatogram. Alright, that's all from me. Thank you.
The first graph, we have standard graphene. We're gonna have to find the response factor. The equation for RF is area of standard peak over concentration of standard in mg over ml. You can find the area of standard below the graph and concentration of standard in your lab manual. So we put it in the equation. The area is 6249.48779 over 0.1. We get 62494.88 for the response factor. Okay, for second graph, we have caffeine in Coke. We're gonna have to find the concentration in ppm. The equation is peak area over F. The area here, you're gonna have to find it in the graph below, the highest peak. So we put it in the equation. 7001.12365 over 62494.88. We're gonna get 0.112 mg over ml. But we have to convert it in ppm. We times the 0.112 with 1000, so we get 112 ppm. Okay, for the third graph, we still have to find the concentration. So we put the area 1.115, 11 exponent 4, and the RF still the same, and we get 0.178 in mg over ml. So we have to convert it in ppm. So we times with 1000, we get 178 ppm. For the average concentration, we have to plus 2 of the concentration and divide by 2. So 112 ppm plus with 178 ppm divide by 2 is 145 ppm for the average.
Caffeine was successfully discovered in the standard and soft drink sample using the Hplc experiment, with value of 2.482 minutes for the standard and 2.481 minutes for Coke soft drink sample and 2.479 minutes for the Levita soft drink sample. The caffeine retention time remained consistent across all tests. The method's stability and the robustness was demonstrated by the minimal variation in the caffeine retention line between the standard and sample. It is common to have a moderate differences in retention time, about plus minus 0.03 minutes, which can be attributed to minor experimental disturbance. The peak area of the caffeine standard was found to be 624.9. Peak areas for the soft drink sample were from 7001.1 for Coke and 1.1151 times 10 power of 4 for Levita. Peak area measurements may be slightly impacted by the irregular sample preparation, which is one possible source of mistake. Apart from that, no correlation for other compounds with caffeine was noted. Nevertheless, this might occur in actual sample and impact peak purity.
In conclusion, the retention time of a standard solution, which is caffeine, is 2.482 minutes. We managed to identify the presence of caffeine in soft drinks by matching the unknown sample compound peak with the standard sample compound peak. We were also able to determine the amount of caffeine in the soft drink sample, which is 145 ppm concentration.